Great. So good afternoon, everybody, and welcome to our webinar today. We're still having some people logging in right now, but I just wanted to welcome everybody and kind of give you a little bit of an overview about what we're talking about today. So we are talking about carbon capture today. I think that everybody should find this quite interesting. The webinar that we're doing today is part of a series of webinars and seminars that 360 Energy is presenting to keep corporate leaders objectively informed about the many changes occurring in the industry that are upcoming. On March the 12th, 360 Energy is sponsoring an executive briefing seminar in Burlington where Bob Willard, along with the Burlington Chamber of Commerce and the City of Burlington, will be looking at the risks and opportunity associated with climate change. For today's webinar, we're very pleased to have Richard Adamson available to discuss carbon capture. Richard's the CEO of Industrial Climate Solutions and is the founding president of CMC Research Institutes, which was formerly Carbon Management Canada. So he works to support collaborative, multidisciplinary research projects aimed at industrial greenhouse gas emissions through a global research network. Richard also assembled the national team that modeled economic ways to move Canada from a prosperous low-carbon future as a part of the 16-country decarbonization pathways project. The Canadian economic models developed under DDPP were influential in provincial climate policies across the country. Before joining CMC, he worked with the Southern Research Institute's Environmental and Energy team in Durham, North Carolina, as part of the US EPA's Greenhouse Gas Technology Center under the Environmental Technology Verification Program. So Richard is, as you can imagine from those qualifications, he's very well briefed and able to talk about this topic. Before we get into that, I just wanted to let everybody know we do have a chat and a question function on GoToWebinar. We do absolutely welcome questions. We will have some time for questions at the end of today's presentation. If we see some really pertinent questions to what we're talking about, we might interrupt, but for the most part, we're going to just hand things over to Richard without any further ado.
Well, thank you very much. This is a real honor to be able to do this, and I had a look at some of the names on the list so that it's a really great cross-section of backgrounds here. I'm looking forward to hearing what the Q&A comes up with. This is intended to be an introductory level kind of a discussion, so I'm going to try not to turn a sip into a waterboarding activity. So if any of the Q&A starts leading me down the garden path into deep waters, I will welcome somebody to throw a flag and say let's keep it light. So this should be a fairly brief overview on carbon capture, utilization, and storage and conversion technologies. So a little bit of an introductory level coverage so that you understand the. I'm sorry, I'm trying to change slides here and my technology is not working yet. So just a moment. There. Okay. So the idea really is to introduce to the concepts and the language and what the ideas are. Carbon capture and storage has been around for quite a while. It went through a surge of interest about a decade ago, and then became kind of a political hot potato, and the tide went out, and things kind of went quiet for a while, at least in Canada and the US. And recently there's been a resurgency around it and a lot of really interesting technologies. This is going to be technologies and projects and policy developments and things. So this is going to be a really important area over the next few years and probably decades if the projections are correct. So we'll do a quick overview, a little bit about the role of CCS in this space. And sorry, I'll call it CCS. Some people call it CCUS. the utilization, conversion, carbon capture, and whatever. So I'll talk a little bit about how we go about capturing CO2, a couple of different pathways. Then deep sequestration, enhanced oil recovery, conversion technologies, and then a little bit of talking about where things are going, in particular in Europe, and some opportunities in North America as we move beyond individual demonstration projects and into incorporating it into an integrated carbon management solution. So this chart is similar to charts that have come up over the last decade, and the numbers always change, but basically this is the IEA's current projection of how we could get to a sustainable development kind of or a sustainable economy in terms of global greenhouse gas emissions. And at this point, they're saying about 9% of the cumulative emissions between now and 2050 will have to be dealt with CCUS in some form. Something that you might want to pay attention to here is in the IEA chart, it shows us getting to 10 gigatons of CO2, but really we need to get to zero by 2050. So that's if we're going to get there without overshoot and having overshooting the 2 degrees Celsius. So this is IEA's projection for 1.8 Celsius future, but it still doesn't get us to net zero. So that chart gives us a 66% chance of getting to 1.8 Celsius. About half of that would come from the power sector and about half from industrial applications. I'm going to mostly emphasize the industrial applications in my comments today. CCS is often associated with the power sector almost to the exclusion of other emission sources, and then it becomes an exclusive conversation around clean coal or extending the life of coal-fired power or that sort of thing, and the politics get really pretty ugly around there. Carbon capture is going to be required on fossil-fueled generating sources, whether natural gas or coal, if we're going to get to net zero. I tend to take a kind of an agnostic approach as to which technologies are going to take what slice of the future. It'll be a matter of what delivers the best economics. Can we do zero emissions power generation from fossil fuels, or is it more economic to do it from renewables and storage and nuclear and whatever the other components will be? So I tend to not emphasize the power sector. The industrial sector, the world is going to need to keep manufacturing stuff, and a lot of the processes for manufacturing stuff involves emissions. And for many of them, we either don't have methods for emission-free manufacturing or production, or the methods are still on the lab bench and we're decades away from doing full-scale implementation. So if we're going to address carbon capture or carbon emissions on the kind of time scale that we're looking at for 1.5, 1.8, 2 degrees Celsius future, then carbon capture is going to have to play a role in there. So in 2050, we're going to have to, by 2050, we're going to have to have captured and dealt with 2.8 billion tons of CO2 per year, which will require 2,000 large-scale CCUS projects in operation by 2040. That's a lot of big industrial processes. Right now, we have 19. So we've got a ways to go. Basically, as I said, we can't afford not to deal with industrial. Whether you're in the camp that says the only path on power is to go all renewable or all nuclear, or some other pathway, whether you like it or not. If we're going to deal with the emissions we're facing on the industrial side, capture has got to be part of it, and this adds up to a lot. Gigatons of CO2 there's very few technologies out there that'll handle that kind of scale. Canada's total emissions is 760 megatons per year, or in 2017. If we ignored the conversion side and just looked at enhanced oil recovery and deep sequestration, there's reportedly 200,000 to 430,000 megatons of CO2, and that's a very storage capacity. That's a very conservative number. There are a number of storage methods that are still being explored, and there's a lot of areas that have not been. We don't have the data to be able to say whether or not there'll be effective storage spaces, because where the seismic exploration has been done, it's primarily been done because of oil and gas. So if there's no hope of oil and gas, those areas have not been thoroughly explored in general. So there's probably a lot more than that available in Canada. Most of it, though, is in the Western Canadian Sedimentary Basin. So it's the Alberta foothills and into Saskatchewan. And there isn't very much outside of that. There is some offshore, both on the East Coast and the West Coast. The Canadian Shield is not a good example of a place to try and sequester CO2. But there's lots of storage capacity, 250 to 500 times the total annual emissions from Canada. If you look back at that earlier suggestion that 10% of global emissions, 9% of global emissions would be handled by CCUS, and wave our hands in the air and say 10% of that 760 amounts to 76 megatons could be handled by CCS. That means that we would have 2,500 to 5,000 years worth of geological storage capacity and potential. So there's lots of capacity. So I'm going to pause there, and before we dive further, is there any comments or questions at that point?
I don't see any questions so far.
Okay, good enough. So we'll talk a little bit about how we go about capturing CO2. We'll talk about wet and dry technology. Later on, I'll mention there's a couple of other ones, but really wet and dry are the two that seem to be getting the most attention right now. There are a couple that are further down the pipe. We'll talk a little bit about size and the impact of different types of emission sources and how it affects the technical challenges of capture, and also a little discussion on cost and how much the costs are coming down in terms of as we learn more about doing this. Okay. All right. There we go. Okay, so this is a rudimentary sketch. I'm not going to go into detail on it, but this is a cartoon of how CO2 capture happens for the industrial process that basically has been around for 50 years or more. The left side is what I call the wet front end. It's the absorber column, and you have some kind of chemical that likes CO2. It's generally referred to as a solvent that absorbs CO2 out of the flue gas. So you run the flue gas through the absorber column and through heat exchangers and pumps and such in between. And on the regeneration side, you then heat this, after the solvent has been saturated by CO2, you then heat it up in a regeneration column to drive the CO2 off. So you wind up with actually wet CO2 with steam, and then you have to dry it and compress it and put it into a pipeline or use it for something. So that's broadly speaking what goes on. Now I'm going to take a brief moment to talk about the technologies that I'm involved in, we're focusing on fixing the challenges of that absorber column with some new technologies to address some challenges. The traditional absorber columns have created limitations in terms of they don't work very well with some of the exciting next generation solvents that are on the lab bench but really haven't made it into the market yet. And there's some opportunities for new chemistry there. And there's a number of other processes that don't involve amine solvents but have other pathways, but essentially all start with a wet front end like this, CO2 getting saturated into a liquid, and then some process on the back end that pulls the CO2 back out of the liquid. It might be biological or chemical. On the dry capture side, Inventus is probably the best example of this. There's other sorbent processes that use this approach. Essentially, there's a dry material that CO2 sticks to, if you want to use that term, and it has a huge surface area. So very small amounts of sorbent have the indication for the sorbent that Inventus or Svante is now using is a sugar cube sized block would have a football field of surface area. So a lot of CO2 can stick to a small surface area. Their process has this rotary system that where a drum is divided up into pie-shaped sections with a lot of fine membranes that are impregnated with this sorbent. And it starts by flue gas flowing past all of these membranes with the sorbent, and the CO2 sticking to the sorbent, and the drum is continually rotating. So once it's finished picking up as much CO2 as it can, it gets around, the drum rotates around, and steam is injected, heating the sorbent up and driving off the CO2. So then again, just like the other process, you wind up with a combination of steam and CO2. You have to then dry it out and compress it. And then the drum continues around, eventually getting cooled off. You have dry, cool sorbent, and it comes back. So it takes about a minute for that drum to rotate around through the process. And they can scale that up to pretty large scale projects. So it's an interesting approach and an alternative to the wet chemistry approach. So,
sorry, Richard. I just wanted to got a comment that just came through. So as you go through these various technologies, would you be able to comment on how much energy those respective technologies would require? Is that something that you could kind of comment on?
And actually, no, I can't off the top of my head. My understanding is that they are getting competitive with the solid sorbent and best of the conventional solvents. The trouble is as they've progressing through these different generations of solvents, and some of them that we're looking at right now, the solvents are inherently 35% more efficient than the last generation of solvents. And efficiency or energy is actually not a very good measure of economics, because if one process requires 150 degrees Celsius energy to regenerate and another one requires 65 degrees Celsius energy to regenerate, there's a whole lot more abundant free waste heat available at 65 than 150 or 200. And so when you get into how much energy is used, that actually doesn't answer the question. The really underlying question is, what are the economics? And then we start getting into how much waste heat is available and that sort of thing. So in order to go there, and I'm not prepared to go there today anyway, but in order to go there would require more waterboarding than tasting.
Okay, fair enough.
Okay.
I have one more question. If you don't mind, since I've already interrupted you.
Well,
So somebody just asked, what's the concentration of CO2 in flue gas before it makes economical sense, or is there any rule of thumb there?
oh, that's a great question to cover in a few slides.
Okay, perfect. Thank you.
Okay. I've got a slide that helps with answering that question quite well. So to give an idea, so this is a CO2 capture plant on a coal-fired power installation. Everybody uses boundary dams, so I thought I'd be different and use the Petronova project in Houston, Texas. So they capture about 5,000 tons a day. So remember that nice little cartoon that showed a regeneration column and the absorber column, and they looked really very similar. Well, that monster structure on the left is the absorber column, and that much smaller column on the right is the regenerator column. So the cartoon is a little misleading on that. And for a brief commercial break, the technology we're working on replaces that absorber column with a structure about half the cross-sectional area and 40% of the height. So we're working on reducing the size of the size, improving the capacity on those absorbers for our core technology. But so this is a 5,000 tons CO2 a day. That's about 90% capture off of a 240 megawatt coal-fired power plant, and that CO2 is used for enhanced soil recovery. That the field was producing about 300 barrels a day previously, and after the started the EOR, they were up to 4,000 barrels a day. So obviously the enhanced soil recovery works really well. There's 80 miles of pipe between this capture plant and the field, and if you look at the emissions on that 3,700 barrels a day of additional emission or additional oil being produced, that would amount to 1,600 to 2,000 tons of CO2 per day in emissions. So assuming that all of that CO2 is going into that field, this looks like it's actually a net negative CO2 emissions, even including the combustion from the produced oil. So the way this project works is the coal plant, the capture technology company, the oil field operator have formed essentially a joint venture. So they all are playing together and sharing in the rewards of it. So in essence, rather than having a bunch of transactions between the capture plant and the pipeline operator and the oil field producer, they basically all joined hands and said, all right, we'll put the costs into a pot and we'll put the revenues into a pot and we'll share. So their revenue amounts to, and $50 a barrel is obviously low, but 185,000, absolute minimum of 185,000 US a day. And that works out to be about a value of $37 US per ton of CO2. If they qualify for the 45Q tax credit, which is working its way through in the US. In fact, I think the rulemaking's just completed on that. That would add another 35 US per ton of CO2. So that's getting to be a pretty reasonable price overall. So somewhere between $75 and $80, $75 and $100 really, depending on the value of oil on this enhanced oil recovery project. So to the question of CO2 concentration and impact, to give people an idea, capture off of, so a cement plant, the CO2 concentration in the vicinity of 20% CO2. Coal plant around 12%. An industrial boiler like the ones through steam generators used in the oil sands, around 8%. Natural gas combined cycle, 4 or 5%. And atmospheric, about 410 parts per million. So if you think about the CO2 as being like a drop of ink in water, going from 1 drop of ink with 4 drops of water down to 1 drop of ink in a quarter cup of water. This is how I sort of look at things in terms of if I'm going to capture a ton of CO2, the size of equipment that I need to do the capture on the coal plant is about 1.7 times as much as I would need for the same ton from a cement plant. And direct air capture, where you're capturing straight out of the air, essentially you have to deal with 500 times as much volume of air as you would volume of flue gas from a cement plant. And it's like putting 1 drop of ink into a quarter cup of water. Now go and get that drop of ink back. So that you can understand that there's a very strong impact on economics based on which sources you have. And some of the industrial sources have got even higher CO2 concentrations to work from. So some of those industrial processes are much more economic. That's not the only factor. Coal-fired power and cement plants also have a lot of other dirty stuff in the flue gas. So there's more cleanup. There's more equipment up front required. A natural gas combined cycle power plant puts out very clean emissions. So although you have to move a lot of gas through your system, at least you don't have to do the front end cleanup work. So it isn't entirely apples to apples, but this gives an idea of qualitatively how the economics would vary from one to another. I'm hoping that's helping to answer. I'm trying not to go into specific dollars and cents, but I've got a chart that gives an idea of the rates on capture over time that I'll show you in a minute, and how much they've come down. Oh, this is it. So there's actually a few interesting things about this. First off, all of the green dots are projects that were proposed and some significant amount of front-end engineering happened, and then they failed to get built. So there's been an awful lot of work in CCS projects that wound up on blind alleys, which is unfortunate, but there was a lot of learning that happened even though they didn't physically get built. This chart is only comparing coal-fired power plant projects, and that's useful because it's really hard to compare economics of a steel mill to economics of a natural gas power plant because the processes are so different. So on the left axis is the number of dollars per ton, US dollars per ton, cost of capture, including the cost of capital and such. So you can see there's a very big difference between Boundary Dam at over $100 and Petra Nova at just over 60. There's a number of projects that are in the queue, including a good reference is Shand on the right. Those blue ones are planned for the future, but Shand is another Sask Power coal-fired power plant. So Boundary Dam was a Sask Power plant, and Shand is based on what they learned at Boundary Dam. This is what they expect their all-in cost would be for capture. So we're something under $50 a ton US for capture on Shand versus over $100 a ton at Boundary Dam. So there's a lot of learning and technical improvements that are happening as we're moving forward. with this. And yeah, as I said, there's numbers on a lot of different projects, but it's most useful to keep a focus on all from similar types of sources. So all coal-fired power plants for comparison here is a little more apples to apples. All right, so we capture CO2. Now what are we going to do with it? You can go from, this chart divides things up a little bit strangely. So you can do, from capture, you can go to utilization or storage. Enhanced oil recovery, I would tend to include it. It could be both storage or non-conversion use, but the economics for enhanced oil recovery are driven by the fact that it's generating value from oil production. On the utilization side, my focus tends to be on conversion processes. Now, conversion processes are unlikely to have the very large volume impacts that deep sequestration or enhanced oil recovery have, but they're becoming more important. And especially if you think about where do we need a lot of something that could actually deal with a significant amount of CO2. So the one thing that we use a lot of is construction materials for the built environment, concrete, gravel, aggregate, those kinds of materials. So if you can develop concrete processes and aggregates that bind CO2, that's a good place to store it. There's a lot of, again, we're urbanizing as we move forward. There's more and more cities being built all around the world, and as that, so that's a good place to put a lot of stuff. Many of the other things that we convert CO2 into may have some economic benefits, but they don't generally have the very high impacts. So some of the interesting pathways, there's some concrete curing applications. They don't generally absorb a lot of CO2, but they do strengthen the cement, and their improvements in the cement or the concrete performance results in use of less cement, the binding component, and it's the binding component that generates a lot of emissions. So while you're not directly storing a lot of CO2, you may be reducing the net emissions from the concrete being produced. So that's an interesting area. Algae cultivation is emergent and developing quite rapidly. You'll read lots of articles about producing fuel from algae or various things like that. The folks that I talk to in the algae sector are not generally pursuing fuels as a primary path because the economics, it's really hard to make the economics work. The things they are pursuing are things like nutraceuticals, spirulina, and dyes, where the economics are much better. Again, not huge impacts in terms of gigatons of CO2, but every little bit helps. On the fertilizer side, in particular, for example, urea is a good pathway to absorb CO2, provided that the upstream processes, you're careful in how you develop the plant. You're not emitting too much in the upstream process. And carbonates, mineralization in general for production of aggregates or other mineral forms. The nice thing about mineralization, and carbonates is another way of talking about it, is that almost anything you can convert CO2 to requires a lot of energy input. If you think about it, you started with some kind of hydrocarbon, and you burned it and got a lot of heat out of it. Well, the reason you were able to get a bunch of heat out of burning that hydrocarbon was the CO2 that resulted has a lot lower energy in content than the hydrocarbon that it started off with. So to try and convert it back to hydrocarbon, you have to climb up a long hill in terms of the amount of energy input that you have to put into it. When you're talking about carbonate formation or mineralization, the amount of energy content in the carbonate form is actually a lot lower than in the CO2 form. So in fact, it's going further downhill and doesn't require a lot of energy input to get there. So carbonate pathways are favorable generally economically, provided you've got a market for your product. So the first path we talk about is deep sequestration. Now, I like this diagram because it starts to get across the idea that sequestration in deep saline aquifers is not, people talk about bury it. Well, that's really misleading. It sounds like it's a few meters down. This is typically, well, it has to be below 1 kilometer. I've had people tell me that it's a good thing we have the metric system because otherwise it would have been below a mile. But 1 kilometer is the regulatory threshold. So deep sequestration is very deep. The Shell Quest project is closer to 2 kilometers, as is some of the deep sequestration associated with boundary dams. So very deep storage, and in what amounts to ancient oceans that are locked up in sandstone or some form of porous mineralogy, with layers and layers of seal levels above it. So it is extremely secure and very permanent. The amount of geosciences work that's been put into understanding every possible risk associated with storage is really impressive. And there's been storage projects running for as long as 30 years in the North Sea. So this is very well understood. The downside is that it's pure cost unless there's some regulatory incentive, some kind of a bounty on the carbon being stored. There's no net benefit to what's being to putting the CO2 down there, except you're getting it out of the atmosphere. My argument is it's not profitable, but garbage collection isn't profitable, and neither is sewage treatment without some kind of regulatory incentives either. Now, I hate this diagram because this is one of those cartoons that implies that everything's happening very close to the surface, and it's not true. But in an enhanced oil recovery type process, the CO2 is used, generally alternating with water, to sweep an oil field that has stopped producing very much. So often 70% of the oil will be left behind in the pore space after the oil production is completed. For the primary oil production is completed, they'll then use a water flood, and then they'll do an alternating water and CO2 at times to get more of the oil out. And so you can really extend the life, as the Petronova project does. What's interesting is you can, during the production process, you can wind up with net negative emissions. Generally, that's not the case. But generally, the way that enhanced oil recovery has been operated in the past, the CO2 going in is a pure cost of production. And so the operator tends to minimize the amount of CO2 being injected. With the right incentives in place, it becomes a revenue source to store more CO2. And therefore, the optimization moves more towards net carbon zero, or even possibly carbon negative during the production scale. What's I find very interesting about this is once the infrastructure is in place with the CO2 pipelines and the injection wells and everything, even after you've stopped producing oil, Technically, you could shut off the production wells and just keep on injecting into those formations for a considerable period of time, decades possibly, after production, and continue injecting CO2 into that space at a very nominal ongoing operating cost. So that's, I find enhanced oil recovery much less. I know that there's controversy about it because you're producing oil that is going to emit, but if you look at the perspective that there is a market for oil, and a barrel of oil produced this way is going to displace a barrel of oil produced by some other means with higher emissions, then this is actually a good thing to be doing. If you assume that the market is being driven by how many barrels are available, and one less barrel on the market is one less barrel consumed, then that's not true, but that isn't the way the market works. So the other pathways is, as I said, transforming it or converting it. Mineralization, production of synthetic limestone. There's a really interesting process by a group out of called Blue Planet out of California that takes concrete rubble, leaches the old cement out, produces synthetic limestone out of flue gas, binding flue gas with the resulting ions. So you wind up with this synthetic limestone aggregate that's very nice and white. And a byproduct is the sand and aggregate that was in the gravel is now available and cleaner than it was when it was first used. So you've got recycled aggregate, recycled sand, and synthetic limestone with CO2 that was bound out of whatever adjacent nearby emission source in their pilot plant there. It's a natural gas-fired combined cycle power plant. There are also other similar mineralization processes where they make baking soda. Precipitating calcium carbonate is basically limestone as well, but it's in a very fine powder form that's used generally in paper making and paints and that sort of thing. So it doesn't require nearly as much energy. The big issue is if you're moving concrete rubble in and moving limestone aggregate out, transportation can be an issue. Works really well in California where they bring their aggregate in from British Columbia and Mexico. But if you've got a mountain of aggregate across the street, like in much of Alberta, it's harder to make the economics work. And their economics work entirely without any value put on the CO2. It's just by selling the aggregate. And there's, as I said, the algae markets. The fuels, dyes, and the fuels and plastics are yet to be proven, but there's a lot more drive towards bioplastics and biodegradable plastics, and in quotes green plastics, and that may start firing up that market. The number of very large scale projects is limited, but I'm not so sure that that's a terrible thing. I think that there's a room in the market for a lot of intermediate scale types of solutions that work for algae or mineralization, for example. So I don't know if anybody's noticed the image in the background that I used on the opening slide. That's a coral reef or coral, and that's actually the original chemistry behind the synthetic limestone aggregate process. So there's a range of different products in there that are that are starting to become more and more common. A lot of this is, as I said, emergent markets. So there's demonstration projects, but they don't tend to hit the news as much because they are often economic at a more modest scale. So the million-ton-a-year coal-fired power plant CO2 capture projects make the headlines, but there's a lot of these interesting conversion projects, smaller volumes, but they're showing some promise as well. So the most exciting thing I see happening in the near term, there's lots of improvements on processes and chemistry and and process economics, as we showed before. But up until recently, everything has been on the basis of a demonstration project. You've got an emission source, some kind of transport system, a pipeline, and then an injection, either deep sequestration or enhanced oil recovery, and that's the project. And every step in the way represents a single point of failure for the project. So there's the risks stack on each other. But in actuality, where we have to be going if we're going to be scaling up at the levels that we're after is integrated systems for managing CO2. So decoupling so that there's multiple emission sources tied into a backbone of transportation systems and a range of different conversion, sequestration, enhanced oil recovery, different types of systems, so that over the course of decades of the life of the system, or centuries, if that's the case, there's as different loads and sources come on and go off, the overall system in aggregate has modest risk and can swing with the punches. We have to be moving into a systems approach. Norway is the first country in the world to really significantly go this way. There's some pieces of that in Alberta, and I think, and I'll talk a little bit about that in a moment. But Norway has seriously signed on to it. The red line there is part of the Norwegian full-scale project. They've got a waste-to-energy project by Fortum near Oslo, where they've got a capture plant. There's a cement plant called Norcem, where they're capturing CO2. Both of those are at tidewater and will have loading facilities where a ship can come by, and I think the Norcem side, they'll have a ship come by every 4 days to load up with CO2. The ships then go around to the west coast of Norway, unload, offload near Bergen, and then there's a kind of a bunkering facility there, and then an undersea pipeline from there offshore, and then there's seafloor injection wells that will inject CO2 into deep sequestration sites. What's really interesting about this was within a few weeks of this project being announced, they started receiving calls from project developers who are looking at investing in chemical plants or various types of industrial projects with 30 or 40-year lives in front of them. They know that there's going to be climate regulation coming up, and they need to mitigate that risk, and they don't know what the policies and regulatory situation will be anywhere. And so they're started calling up and saying, if we develop our plant in Norway, can we participate in this and manage our CO2 risk for the life of the plant? I think that's really significant. The other thing is all of those blue dots are groups that have signed on as conceptually. So Heidelberg Cement is the parent of Norcem. Norcem years ago declared that they were going to be net zero emission cement supplier within 30 years. Heidelberg Cement patted them on the head and said, that's nice, you go ahead and do that. But now that this project is moving, Heidelberg is one of the largest cement producers in the world, is now essentially going through and looking at every one of their plants at tidewater in this area to evaluate which ones are going to be the next ones they put capture on so that they can participate in this project. And so this just shows projects all over the European basin that want to tie in and inject CO2 into those spaces. The green lines, Acorn and Net Zero Teesside, are similar regional gathering systems with their own offshore injection, and so the CO2 could go in either direction there. But this is an example of really looking at CO2 management on a systems basis. And other places in the world are looking at hubs and systems approaches, including in Alberta. We do have the Alberta Carbon Trunk Line. which connects a couple of sources to one enhanced oil recovery field. The reason I hesitate to call it a real integrated carbon management system is it is close to the Alberta industrial heartland. It actually goes through that area, but there is no gathering system associated with it. And you could pretty much stand on that pipe and throw a stone and hit the ShellQuest deep sequestration pipe, but the two aren't connected to each other. So we have a lot of the parts and pieces that could become an integrated carbon management system, and we could integrate a number of emission sources in the industrial heartland. We're not quite there yet, but we have a lot of the pieces. I won't go in any further, and I guess now's a good time to open up for questions.
All right, thanks, Richard. Yeah, we've got another question here. We'll see if any others pop up. Just a reminder for people, just to kind of keep low on background noise, we encourage everybody to ask questions through the question function on the webinar menu. So one question we've got here, does amine solution have any co-benefit? For example, does it remove any other pollutants in the flue gas at all?
Yes, but probably more importantly, if you've got, and it depends on the pollutants you're thinking of, generally a lot of the pollutants that are, for example, sulfur or particulates or mercury, those kinds of things have to be scrubbed out before you get to the CO2 capture plant. So if we, let me see it, if you look at that, at this plant here at Petra Nova, the facility on the left, to the left of the big column, is actually pre-cleanup facility as well. So, and in Boundary Dam, it's even it's quite a bit larger, so that it's got a sulfur removal component. So the net effect of a CO2 capture plant is extremely clean emissions. Some components get scrubbed in the CO2 capture, but if the components are heavier than are more than fairly small amounts, then generally they have to be scrubbed out before the CO2 capture. So the net effect is always extremely clean, clean resulting flue gas.
Thanks for that. We've got just another question from somebody in the office with us here.
Can you just speak a little bit about what are the emissions? Once you've put the emissions through that scrubbing process and then the CO2 capture takes place, what are the remaining things left over?
Well, first off, generally capture is generally captures 90% plus is generally the target for CO2. So a small amount of the CO2 remains, of the order of 10%, and otherwise it's generally water, nitrogen, water, and some. There is also some. There can be some amount of amine carryover that has been raised as an issue, but the CCS plants that are designed currently generally have a water wash or some other form of system to eliminate the carryover of any of the solvent.
All right, thank you. Got another question that's come up. What do you think it will take for an integrated system to be developed in Western Canada?
We're actually very close. There's and we're in conversations right now. So I don't want to. I think the conversation needs to develop further. Part of it would be some kind of an incentive. The U.S. regulation, the 45Q tax regulation, which provides a substantial value on tons of CO2. I call it a bounty on tons. In their case, it shows up as a tax credit. It could come from another form, but there needs to be something that increases the incentive for sequestering the CO2 to get the CO2 out of the way. I also think that in addition, so the Alberta Carbon Trunk Line is a great start in that it's a high capacity backbone, if you will, but we need the ribs as well. We need the gathering system in the industrial heartland. And what I would suggest, and the conversation I've had with some of the major utility operators, is around the possibility of structuring some kind of a low risk, long-term contract for operating such a facility, a system, so that the gathering system could be handled. So I've interviewed engineering firms and industrial developers, both in Canada and the UK, around carbon capture. And one of the comments that I thought was really pertinent from the engineering firm in a major engineering firm in the UK is that several of their customers have come to them and said, "Look, we're interested in putting carbon capture on our plant," and they get deep into the how. And then they get up to the point where the pipe gets to the fence line. And as soon as they find out that there isn't someplace on the other side of the fence to take it away, they stop being interested in doing it. So there needs to be infrastructure that deals with the CO2 outside of the plant. Industrial plants are often willing to invest in the carbon management side of it, but they don't really want to do the pipes and the injection wells. And Shell Quest is fine because Shell does pipes, Shell does wells, Shell, they could handle it end to end from the refinery to the well. But generally, if you're going to have an integrated system, you're going to have emission sources, and they should not have to worry about what happens beyond the fence line. You have to figure out how you're going to handle the transportation system, the gathering and long-term transportation system. And then you've got to figure out how you're going to incentivize the usage and storage and sequestration side. And so it's a complex problem, but technically we've got most of the regulations required, for example, for enhanced oil recovery and deep sequestration in Alberta. And we've got a good chunk of infrastructure already in place that we would have to build on it. So yeah, probably too much detail, but it's I think we're a lot closer than perhaps we give it credit.
Richard, Dave Arkell here. What you're describing, and I suspect, is it possible to have a national utility that actually collects CO2 and then pipes it to Alberta or other locations from the industrial? Is that, I'm just wondering about the economics. Is that something
I'm glad I'm not the only completely nutso person, but what my argument, I don't know enough about pipeline economics to be able to say whether it's practical or not. But one of the arguments I have been making is if Alberta is absolutely bent on making sure that we get pipelines to market for petroleum products, maybe we ought to be building CO2 pipelines in parallel with the oil pipelines to bring the CO2 back from central Canada. I'd really like somebody who knows a whole lot more than I do about pipeline economics to figure out how completely crazy that is. But it sort of makes sense in concept.
You'll be pleased to know there's a couple people from pipeline companies that are online, so maybe they'll start doing some math on this right now as we talk. But I'll hand it over to Julie.
Yeah, so I guess that's maybe a good point to end on, especially since we're at 2 o'clock as well. Richard, thank you so much for a very informative webinar today. We really appreciate your time in preparing this and doing this. Just for the audience at large here, just wanted to let you know the taped webinar today. We should have that available online for viewing. I know some people had to step out partway through, so hopefully those people will be able to get some value out of watching the taped webinar as well. But yeah, without any further ado, if you do have any further questions or want to reach out, feel free to contact myself or Tom Brown, who are the people that kind of organized things today. You might have seen some communication from either one of us. And yeah, once again, thank you so much, Richard. And yeah, I appreciate everybody's time today. Thank you very much.
Well, thank you.
Have a great day, everybody.